Okay, so yeah, so kind of maybe just for the purposes of warming up, in 14.1, I've just found a problem, 71. It's a double integral, and it is x cubed plus 3y squared. And then, so that's the function I'm integrating, and the bounds are, or the order of integration is dy dx. And that means we're going to work on an inner integral with respect to y, then we do an outer integral with respect to x, and we work our way inside out. The bounds for the inner integral are x squared to 2x, and the bounds for the outer integral are 0 to 2. And so, now what's funny about these directions here is they asked me to use a computer algebra system or use some technology to help me do this integral. I kind of didn't think I needed that, so that's why I grabbed it. I think I can do it without technology. So let's work on this. I'm working on the inner integral. Again, I mean, there's kind of always two things. How do you do this? And so this is how you do it. You work your way inside out. Now you're integrating with respect to y. That means you're treating x's like constants, and you're integrating, and y is the variable, x is a constant. It takes a little getting used to. If this is a big old constant here, when you integrate with respect to y, I think you get x cubed y. When you integrate him with respect to y, you get y cubed divided by 3. Right, y cubed and 3's cancel, so you just get y cubed. So, cool. The inner integral is finished. The inner integral is finished, except it needs to be evaluated from x squared to 2x. And now you're plugging in these bounds for whoever was just the variable, and the variable was y. So you're plugging these bounds in for y. So here we go. This is going to take some algebra here. An x cubed times a 2x plus a 2x cubed. That's what happens when you plug that in for y. Minus, now you're plugging x squared in. X cubed times x squared plus x squared cubed. Cool. That's what you do. You plug in your upper bound, you plug in your lower bound, you subtract them. What's interesting is all the y's are gone after this step. There were x's and y's in this problem, but after this step, the y's are all gone. It's just going to be a function of x. Let's clean it up. That's 2x to the 4th. That's 8x cubed. That is x to the 5th. Wow. And that is x to the 6th. Interesting. There's no like terms there, so I'm finished with the inner integral. And so what's left is an outer integral from 0 to 2 with respect to x. That's what's left. The outer integral from 0 to 2 with respect to x. By the way, there is no y's now, so it's just a normal single integral. It's kind of a large one here, but we can handle it. It's easy little power rules. 2/5 x to the 5th, 2x to the 4th, 1/6 x to the 6th, 1/7 x to the 7th, evaluated from 0 to 2. When I plug in the 2, that's going to basically be my answer. When you plug in the 0, you're going to get a bunch of zeros. So plugging in a 2 and working on this is the fun part. 2 to the 5th is 32. 2 to the 4th is 16 times 2. That's 32. 2 to the 6th is 64 sixths. 64 sixths. 2 to the 7th is 128 sevenths. All right. Anyway, that's my answer. Yeah, I don't really care. I mean, you should clean these up. I'm kind of bored. And I forgot my calculator. Is that what I did? Yeah. So, rather than show off my common denominator skills, I'll just let you tell me whatever that is. But it's a number. Can you tell me what it is? Or you can just pick up a calculator and it's going to be so many sevenths maybe, or I don't know what the common denominator is, 21 or... Give me a decimal. give me whatever you want. I'll just patiently wait.
52.41904762.
52.4190, blah, 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 blah. Okay. Anyway, can you hit your fraction button and make that a fraction?
I don't even think this one has fractions. Maybe.
You know how to find your fraction button? Underneath math. You go to math, and you hit that. It's the top one. You hit enter. You hit enter.
5504 over 105.
5504 over 105, and that is that, huh?
Yep.
Okay. So I call this exact. I call this approximate. Why did you say ooh? Did you just learn about your fraction button? That is cool. I mean, right, you can have, if it's a famous fraction in decimal form, your calculator will find it for you, right, with that fraction button. So you knew this one, huh? And also if you don't round it too much. So you kept this nice and you had this in your calculator, but you hit your fraction button and it showed you this, huh? Yeah, cool. Anyway. Now, okay, so so that's how you crank out a double integral. Again, I'm repeating myself from my last two lectures. I mean, this is, we've done, I need to kind of move on, but, you know, how do you do a double integral? Okay, we've done that for a couple days. Here it is, the third day now. And then what does it mean? We've done that for a couple days too. Can you remind me what that means? What is this number?
That's the volume.
It is. And let's talk real specifically here. It's the volume between, and maybe I should even get real technical and call it the net volume, although, because I'm worried, remember, these integrals, they treat volume below the xy plane as negative volume, volume above the xy plane as positive volume. Ultimately, we got a net volume of 52 here. But the truth is, now that I know this shape, this shape is above the xy plane. So it's the volume between the surface. And by the way, what is the surface I'm integrating? The surface is right there. The surface is this z equals, or f of xy equals x squared plus, x cubed plus 3y squared. Oh yeah, I just misspoke. Actually, some of this, because of that x cubed, yeah, some of this could be negative, perhaps. We could have some. But anyway, so it's the net volume between this surface and the region R in the xy plane. The region R in the xy plane. And the region R in the xy plane is described in the bounds. Described in the bounds. But I want to go a little further here, so I just wrote a sentence to tell you what this answer means. But I want to specifically talk about this region. What is this region specifically? There it is. What this region is it's, what we said was that the y lives between these two functions. So I have, as a lower bound, I have y equals x squared, and as an upper bound, I have y equals 2x. Let me graph those. Well, we know what y equals x squared is. This classic parabola. This is a big blown up version of it here. We know what y equals 2x is. It's a line. It goes through the origin and it goes up 2 over 1, up 2 over 1. So I think, what was this? This x squared was a lower bound. Remember that? How come I said that? Because it was the lower bound, and the upper bound was this guy. So my y values live between there. I got them written backwards here, but the x squared is the lower bound. The line y is the upper bound. So my y is varying between these two curves. And as y varies between those two curves, what's x doing? Because these are the bounds for x here. What's x doing? 0 to 2, and that's a left and a right. So the furthest left is x equals 0 right here, and the furthest right is x equals 2 right here. So with this top, this bottom, this left, this right, This is a picture of the region over which I'm integrating. And that's what we do with double integrals. With double integrals, we integrate over a region. Do you remember the good old days when you just did a single integral and you went from A to B? Remember that? You know what you were doing there? You were integrating over an interval. On the x-axis, you were integrating from A to B. You were integrating over an interval on the x-axis. Well, now we're integrating over a region, and the region is described with these bounds, and it's a double integral. We're integrating a 3D surface over this region. And we just found the volume between that 3D surface and this region. 52 point whatever. You know, I'm over here where in quadrant 1 where x and y are all positive. If x and y are all positive, I believe these z values are all positive. I believe this, whatever this function is, it does live up above this surface. It's pretty damn steep too, by the way. There's a lot of volume, 52 units, cubic units of volume between this surface and this skinny little region. There's a lot of volume here, probably pretty high up here. So, good. This was kind of a repeat. I mean, it was a new problem, but it was kind of a repeat of Wednesdays and Fridays discussions about what we're doing here. Any questions? Did you want to? Okay. If I ease into 14.2, I maybe can find a cool problem, but I maybe already did that a little bit last week. Yeah, this stuff starts to get good, guys. Really good here. Wow, check this out. Let's do this problem. I'm in 14.2. I'm going to try this, number 30. 14.2 now. Number 30. All right, so here's what it says. 14.2 says, number 30, set up and evaluate a double integral to find the volume of the solid. The volume of the solid, that's the appropriate language, bounded by these graphs. So in number 30, I've got y equals 4 minus x squared. And I've got z equals 4 minus x squared. And I also got the little statement that I'm in the first octant. Okay. Well, you guys, these equations are 3D shapes. I'm in the first octant, and they form the boundaries of some 3D solid, and they want the volume of this solid. I can do volume with a double integral, but I got to know what I'm doing. I mean, the main thing I need to do volume is I need to figure out the region over which I'm integrating, and I need to know who am I integrating? What's my ceiling? What surfaces am I integrating? What's the upper surface and what's the region in the XY plane over which I'm integrating? That's the main things I got to figure out. So I need a good picture of this. And that's going to be part of the big challenge coming up here for you guys, is drawing these pictures. So let me help you. So we discussed drawing this. I would categorize and call this a cylindrical surface. It is not a cylinder. Do you recall why I call it a cylindrical surface? Because it has one of those missing variables. When it has a missing variable, it fell into the category of cylindrical surfaces. We studied them a little. I never did make you work too hard or give you an assignment here, but we studied them a little. I would call this, I would call it a parabola that hits the z-axis at 4 and comes down and hits the x-axis at 2 and -2, except because I'm in the first octant, I'm not going to go look at the negative aspect of this. It's coming down and it hits the x-axis at 2, the z-axis at 4, and look, who's missing here? The y variable is missing. If the y variable is missing, this shape runs parallel to the y-axis. So it runs forever parallel to the y-axis. That's that shape. And that's probably my surface. I mean, when I go to set up a double integral, that's probably who I'm integrating. I mean, you know, again, this is z. I mean, you're integrating z. And it's the ceiling, and there is no other z in this, you know. So this is who I think I'm integrating. I'm integrating this z, 4 minus x squared. But that's z. It's not the other. It's not the other 4 minus x squared. You know, maybe I should sketch this other thing. This other thing is also a cylindrical surface, but it's missing z. You know what it does? It hits the y-axis at 4. And the x-axis at 2, I'm pretty sure. See, this is this parabola, you guys. Look at this. This is this parabola sitting here in the y-x plane. I don't care to go back toward those negative, you know, it does come back here, but I don't want to look at that negative. I'm only in the first octant, so I don't want to go back to that negative octant. And then, so it's this parabola, y equals 4, and then since z is missing, it's running parallel to the z-axis. Holy shit, you ready? That means this runs up, it's going to hit there. Dude, listen, I'm trying my best to draw and describe, but this top is coming curving down toward me like this, all right? And then this side wall is curving this way. So I feel like I got this side wall that's this curving parabola, and then I got this ceiling that's this curving parabola. Now listen, they're going to meet. And so watch when I draw this, the whole shape comes into play, comes into picture here. There's a crease where this parabola hits this parabola, and there's a little crease. I think it might look like that. I think this is coming down at me. This is a side parabola. I like this. This is coming down at me. That's my ceiling. I'm integrating. I'm integrating that function. This ceiling here is z equals 4 minus x squared. This side wall right here is y equals 4 minus x squared. How you guys doing? I'm making sense, huh? So I went to the trouble of drawing a great 3D picture here. I feel like I kind of needed to for this problem. But really, here's what I really needed. I needed to figure out who's the ceiling, which I already kind of had figured out. And then what I need to figure out the region over which I'm integrating. That's the key. The region over which I'm integrating dictates these bounds. Well, the region over which I'm integrating, I can see it right here. It's down here in the floor. In fact, what I really want now is a 2D picture of that region. This is the y-axis, this is the x-axis. It hits here at 4, it hits here at 2, and it's this parabola. This is the region over which I'm integrating. Okay, now listen. Once you decide the region over which you're integrating, then you get to decide, should I do this dy dx or should I do it dx dy? That's what this dA is. This dA is dy dx or it's dx dy. It's your choice. And it depends it's the order of integration. Who do you want to go first? And the truth is, with a picture like this, it hardly matters. X could go first, then y, or you could let y go first and then x. We're all more comfortable letting y go first and dealing with this function y as a function of x. So if we let y go first, who is the lower y? Y equals 0. Who's the upper y?
4 minus x squared.
y equals 4 minus x squared. So we go from, so our bound, so I decided I'm letting y go first. I'm going to do x next. And the bounds for y are 0, y equals 0, to y equals the parabola, right? 0 to 4 minus x squared. After y does that, I need to let that y stick that's doing that move this way and take care of all the x's. All the x's from 0 to 2. It takes me a long time to talk it out and think it out. I mean, it's hard. I don't know. It's hard to explain all this. I mean, I'm teaching you the methods and the ideas. I didn't need this good of a 3D picture. I really didn't. I just needed to figure out who was the ceiling, because the ceiling is who you're integrating. But we all knew it was z, so we knew that. I needed a good picture of the floor. I need the ceiling and the floor, kind of. And so I got a good picture of the floor. That helps me set up these bounds. And now we can do this problem. We could find this volume. We could find the volume of this nice wedge of cheese. Doesn't it look like a nice wedge of cheese? Or something? Got a wedge. Any questions on that setup? Well, okay, should I finish this? Again, I keep thinking, sometimes I don't have to finish these. You know, and in fact, part of your exercises might be to set up and not finish. You gotta be able to integrate and finish some of them. Do you guys care if I finish this one? It's a pretty easy one. You could probably do it. You know what? Well, I'll finish it. You know, I want to integrate with respect to y, so I could write 4y minus x squared y if I integrate each term. But the truth is, you know, what if I thought of this as one big constant? I could think of it as 4 minus x squared times y. You know, in other words, I kind of factored the y out, I guess. And then if I evaluate from 0 to 4 minus x squared, this is kind of funny, but this is going in for this y. So now I have 4 minus x squared times 4 minus x squared. And I want to integrate that with respect to x from 0 to 2. I mean, you saw how quick this goes? That was, the inner integral was done. The inner integral was then evaluated. And here I am ready for my outer integral or second integral. In order to finish, you should FOIL it out, integrate. You should FOIL it out, integrate, and evaluate, I guess. Let me help you. On your mark, get set, go! 16 minus 8x squared minus x to the 4th. Wow. From 0 to 2. I'm going to now integrate 16x minus 8/3 x cubed minus 1/5 x to the 5th from 0 to 2. Everybody knows the answer is 32 minus 64/3 minus 32/5. And everybody knows that's really just 128/15. Am I right? If I'm right, this was a total luck. At the end, I guessed. Don't. 16x. Integrate.
Yeah, 64 over 15.
Oh, it's 64/15?
Let me double check.
Oh, no, sorry. That's okay, because I totally guessed at the end. I did that right, didn't I? You did that right.
Plus next. Like 4 and 16, 15, so long.
Yeah, 64 over 15.
So your answer.
That's the answer. 64/15.
Woo!
What is it? It's the volume. Volume of this? Dude, this is a wedge of cheese. It's 64/15 cubic whatevers.
So how did we find the x boundaries, 0 to 2?
This picture, which came from this picture kind of, but the region over which I'm integrating in the first octant was the floor of this. See, what's confusing, I'm dealing with two, they're both the same equation, but with the z equals, that's this ceiling parabola coming down at me, and then this other one is sort of this sidewall parabola. but then the region over which I'm integrating is this region in the floor here, which I drew here, and this is where, see, when you set up these bounds, you let, the first guy is very arbitrary, so his bottom is, well, it's not too arbitrary, his bottom is clearly 0, and then his top is this function, which we arbitrarily call this function. We don't say 4, we say anywhere on this function. Could be here, 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 could be here. Right. So the first bound is kind of this arbitrary, this y to this y. Then the last bound is it should be numbers. There shouldn't be, the last bound is not variables. The last bound should be numbers. So you go from the extreme left x to the extreme right x, 0 to 2. Right. 0 to 2.
So I guess like when you graph 4 minus x squared, it should give you, it should graph it from 0 to 2, and that's how you know the x value.
Well, I mean, right, when you graph 4 minus x squared, it's a parabola, it's an upside down parabola. Yeah. But you know, it's actually that. Yeah. But they kept, we were in the first octave, so we were half of this parabola, we were on this half. Right? Yes?
Where did you get,
I foiled this out. Oh, I did screw up. That last one's
okay, that's why.
Yeah, that's a positive x to the 4th. Sorry about that. Right? When you foil that out, I screwed that up. This is positive, this is positive. Maybe there's a different answer here.
Actually, I don't remember what it is. Explain what my calculator is. It's green.
Yeah, good. I screwed that up. Right. You guys right? Too fast. I was going too fast.
I'm getting 256 over 15 now.
Right now it's 256. All right, thank you. Okay, that's better. Thank you, thank you, thank you. I need that. I'm really hauling ass. I need help. All right, let's do this. Let's try to do this. So I'm making up this problem. I want to find the volume of a sphere. I want to find the volume of a sphere of radius A. Okay? So, anybody know the answer? Anybody know the answer? Do you know the volume of a sphere of radius A? If you know the formula, you're excused from this problem. No, sort of kidding. Anyway, oops, the answer is 4/3 pi and the radius cubed. My radius is A. So there's the volume of that's the volume of a sphere. 4/3 pi r cubed. Radius A, it's 4/3 pi A cubed. That's the volume of a sphere. In case you might not have known that. But what I guess I'm asking you to do is prove it with a double integral. And so we need to do a double integral. All right. So I need to think about what I'm doing here. A sphere, you know, in 3D here, I'm trying to do a sphere, radius A. Let's center it at the origin, please. So do you know its equation? Do you know the equation of a sphere centered at the origin, radius A? Do you know what its equation would be?
It was x times
x squared plus y squared plus z squared equals a squared.
Good job. Yes, that's a sphere of radius A. Yep, that was from chapter 11. We knew how to do that. All right, all right, all right. So I'm going to be, that's the name of that surface. Let's see. If I'm setting up a volume, you know, I'm doing volume with a double integral. This is what I'm doing. Then I need Z. I really need Z. So help me think this through here. I'm setting up a double integral. So who do you think I'm in? I guess I need Z. I guess I need to solve for Z. What would Z be?
Positive square root of a squared minus x squared minus y squared, but all that square root.
Okay, he's right. He did move the x squared, move the y squared over, take the square root. If you take the square root, you get that plus and minus square root. The plus square root is the top hemisphere. The negative square root's the bottom hemisphere. So maybe we'll just work on the top hemisphere and we'll multiply by 2. So anyway, so he was suggesting there that when I solve for z that I just take the positive square root. So it's the positive square root of a squared minus x squared minus y squared. And so that's the name of this top hemisphere. Okay, so you're saying that's what I'm integrating. That is what I'm integrating. A squared minus x squared minus y squared. Okay. All right. So you're totally right. Now, here I go. I got to do this with respect to y and with respect to x, I guess. I think I'll do dy dx. All right. And now, wait a minute. Are you guys saying we should multiply by 2? Should I put a 2 out front? Because I'm not going to do the bottom half, right? Is that what we're saying?
Yeah.
So I should multiply by 2. Or wait a minute. All right, so now I want to work on my bounds. And if I want to work on my bounds, then I want to work on the region over which I'm integrating. I can sort of see it there, but I want to see it clearly. So the region, so I also draw this 2D picture of the region over which I'm integrating, which is this floor, which is a circle of radius A.
Yep.
And what's the equation for a circle of radius A? By the way, maybe you know the equation of a circle of radius A, but maybe you also know that if you take this sphere and let z equal 0, you're in the xy plane. If you let z equal 0, and what do you have?
The equation of
X.
sphere with radius A.
Right. Circle of radius A, right.
Oh, yeah.
Yeah, right. Circle, sphere, I know. So we could do this whole thing. You know, the truth is, what did I say? Let's just do the top half and multiply by 2. Maybe you want to just do this corner and multiply by
I think so.
4
8.
or 8 now. Okay, you're right. Hang on. You're saying, I already said I'm just going to do the top half and multiply by 2. And now I'm saying, let's just do a fourth of that. So you're saying multiply by 4 also. So we're doing an eighth of the sphere. We're going to work in the first octant, and we're going to do the an eighth of this sphere and multiply by 8. Okay, beautiful. Good idea. All right, so now there I am. So I need to come up with bounds for x and y, and y goes first. So what would y do here? Your y bounds would be?
A squared minus x squared positive square root of that.
Okay, hold on. Your lower bound would be y equals 0, I think.
Yeah.
And your upper bound would be y equals whatever this is. And he's saying we got to solve this for y in terms of x, is what he's saying, right? And so that would be y equals, if I solve for y, the square root of a squared minus x squared. Yeah. Hey, the square root of a, that's a semicircle, that's the upper semicircle with the positive square root. The negative one is the bottom semicircle. But we could just do the positive, we could just go to that one. We can go from y equals 0 to this square root of a squared minus x squared. Cool, dude. And what about bounds for x?
0 to A.
0 to a. 0 to a. Bounds for x. Y is doing this. While y does that, x has got to go from 0 to a. Okay. All right. I swear to God, if you do this, the answer will be this. But I guess you're supposed to prove it or do it. So all of a sudden I got to integrate with respect to y. Holy shit. Oh. You guys know how to integrate with respect to y?
You'd have to rewrite
Yeah,
that.
it's going to be a U substitution thing.
It's going to be worse than that. It's these damn circles, man. I'm telling you. Do you remember? How would? Okay, in Cal 2, you learned how to do this integral. And by the way, this is a circle. This is a semicircle, radius 3. Blah 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 blah. In Cal 2, you learned how to do this integral. Do you remember what you did?
I think you would rewrite it as 9 minus x squared to the 1/2. and-
Well, that's okay. And then what? Because that doesn't help that much.
Right, right.
For that one, couldn't we just do?
See, this is what you were talking about this Friday. How do you do this integral from Cal 2? There's only one way to do this. Trig substitution. Let x equal 3 sine theta. Dx is 3 cos theta d theta.
Right.
I
You
got
draw
it.
the triangle.
This is old, you draw a triangle. This is old trig substitution method. It makes everything, it turns it into a trig type integral. Then we got to know how to do, I think we end up with a cos squared in here, so then we got to know how to do cos squared, which is a special half angle formula. There's a lot to know, and about a page of work, or half a page, to finish this problem. And that's called trig substitution. It was complicated and cool. It was cool. I liked it. Well, I kind of got to do that here. See, hang on. Who's my variable in this problem? My y, right? For the inner integral, my variable is y. And so this is a big constant. So this is like my 9. This is like my 9. So I got to let, what the hell? I got to let y equal the square root of a squared minus x squared sine theta. Treat this like a constant. This is my trig substitution. This is, I'm not lying to you, but I am sort of pulling your leg. I think that means lying. No, I'm not lying to you, but I'm not going to.
You should there's like a shortcut to it.
Yes.
Yeah,
There is, no, listen. This is lengthy and horrible, and maybe I should make you do it to see how lengthy and horrible it is. But, do you think it's lengthy and horrible? Do you agree? Okay, then I don't have to do it. Okay. All right. So the truth is, this is leading me into. Go ahead. What do you want to say?
Well, I mean, couldn't we treat because a squared minus x squared is a constant,
Right.
sort of.
Right.
Couldn't we treat that as a difference of two squares, then turn it around, or say turn it around, so that you'll have like a, and then take one of the two of those, change. Where was I going with this? I had an actual mathematical reason we could do this, but somehow change the constant so that it was, oh, right. So pull out a negative so that it was squared, cancel out the square, and then factor out the I all the way out. So that it's 8 I goes to the rest of it. And then integrate with respect to y.
I don't think so. Explore that on paper and see where it leads you. Someday. Not right now. Okay, explore that on paper and see what happens. So I'm telling you how to do it. This is how to do it. It's called trig substitution. This whole problem turns into, it looks like an algebra problem, it turns into a trig problem. And it's from 8.4. It's a method of integration. And now so that's how to do it. Now extend that into our world. My 9 is my a squared minus x squared. My variable is y squared, and so I'd have to go with this, I'd have to do this. My dy turns into, this is a big constant, cos theta d theta. I have to shove all this in here and watch the purpose that the radical will clean up. That's the purpose of this trig. So this is actually how to do it, and it's horrible, kind of horrible. So I do have a better way. And anyway, in your way, I don't think was a way, maybe, but I'm not sure. But anyway, so this is the way, but now I have a better way, and that leads me into 14.3, where we do this. We switch to polar coordinates, and this is powerful, and this is a blessing, because when you switch to polar coordinates, this is a hell of a lot easier. You really, and switching to polar coordinates is like switching to trig. So it's in a way it's similar to this, but it's better than this method of trig substitution. The whole problem is going to get switched to polar coordinates. So now I feel like I better remind you a little bit about polar coordinates, shouldn't I? Let me remind you about polar coordinates. So now I've got to get back to, I'll get back to this. But now I've got to remind you about polar coordinates just for a second. Listen, polar coordinates are, we had an x and a y axis. And if you wanted to get to this point, you called it x, y. You know, how would you get there? This is, you move over x, you go up y, you know, and you land on this point. That's called rectangular coordinates. X's and y's are called rectangular coordinate system. Okay, you can switch x's and y's into a polar coordinate system with r's and thetas, where instead of going over and up, you do this. You rotate the angle theta, and you walk out the distance r. And you get to this point, and now it's got a new name, r theta. You can get to places in the xy plane using r's and thetas. It's a new coordinate system. It's called polar coordinates. Instead of rectangular coordinates or x's and y's, you know how they work. Polar coordinates are r's and thetas, and I just sort of showed you how they work. Theta is measured like this. R is a distance out from the origin. What you learn from this picture real quick here is that this is x, and this is y, and this is theta, and this is r. So what you see here is some relationships. This is a beautiful right triangle trigonometry here. And what falls out of this is some relationships that help you convert from x's and y's into r's and thetas. The classic thing you see first is that x squared plus y squared is r squared. That's a classic, that's true. If you want to convert from x's and y's into r's, this is true. Here's another one. The tangent of theta is y over x. Or in other words, maybe if you want theta, you do the tangent inverse of y over x. But I'm trying to show you, this is how you can get r and theta. Given an x and a y, you can convert to r's and thetas. Here's something else that falls out of this picture. So this is some formulas. They just fall right out of this picture. You see them, right, you guys? You see them? These aren't mysterious. Yeah. Watch this one. This one's not mysterious either, but watch this one. The cos of theta is adjacent over hypotenuse, x over r. What we prefer to do here is multiply by r, and then we have this equation. X equals r cos theta. Similarly, y equals r sine theta. Would you agree? Awesome. Those are awesome. In fact, to switch from x's and y's into r's and thetas, this is kind of what you use. You go, turn all this into x's and y's. I want to get back to my problem. Maybe I'm ready to. I mean, there's a whole, I could have huge discussions about polar coordinates, I suppose, but in a way, this picture and these equations that fall right out of this picture are the gist. And it helps you convert back and forth from rectangular to polar, from rectangular to polar. See, polar coordinates are awesome when you're working with circles. See, you get it, right? Look, circles. They have this beautiful equation. Well, until you try to solve for y and make it a function of x, then look what you get. You get this damn square root, and you can't integrate it. When you can't integrate a circle like this, you got to switch to polar coordinates. I mean, you got to switch to, I mean, circles are horrible in rectangular coordinates. They got these nasty square roots. They're not nice. Circles are awesome in polar coordinates. Watch this. If this is x squared plus y squared equals a squared, if that's the name of a circle of radius a, let's convert this into polar. What would his name be in polar? Well, according to this, x squared plus y squared is r squared, right? So I'm replacing this x squared plus y squared with r squared equals a squared. Or take the square root of both sides and you get r equals a. You know what r equals a is? A circle of radius a, centered at the origin. Are you guys with me? I mean, right, here's a circle of radius 3 centered at the origin, right? A circle of radius 3 centered at the origin. If you solve for y, you get plus or minus the square root of 9 minus x squared. That's your upper semicircle and your lower semicircle, you know? It's a pain in the ass. Okay, now let's convert them to polar. X squared plus y squared is r squared. R squared equals 9 is the name of this circle. But actually, let's solve for r. Let's take the square root of both sides. We don't need the plus and minus for this, I'm sorry. R equals 3 that's the name of a circle of radius 3 in polar coordinates. It's beautiful. Simple. So the big idea then is, I'm sort of reminding you of polar coordinates at the same time. I'm trying to do double and triple integrals, but here's the idea. When we're integrating over a region, and our region is circular, let's switch to polar coordinates. That's it. That's the idea. Let's not deal with x's and y's and nasty square roots. Let's switch to polar. Okay, now what does that mean? Okay, watch. Everything's got to switch to polar. And in the double integral, here's what that means. The dA, this is interesting right here, and I can explain this someday perhaps, maybe not now. The dA, in the dA, what is dA been in our problems? It's either been a dy dx, or it's a dx dy, right you guys? Okay, guess what now? It could be in polar coordinates. And in polar coordinates, you probably might guess, oh, it's dr d theta. Well, sort of. There's an extra little r that comes with it. It's actually r dr d theta. The dA in polar coordinates is r dr d theta. It's no longer a little rectangle. You know, the dA with the back in... So little time, so much to say in so little time. You know, the dA was this little chunk of area. This was our little dA right here, and it was this little change in x times, it really was like a length and a width of a little baby rectangle, and that's why it was dA, and it totally made sense. Okay, well now, they're not little rectangles anymore. The dA is now, if we switch to polar, the dA is now sort of, it's a sector of a circle. It's this. It's a sector of a circle, and this dA in polar coordinates, and I'm not really explaining the geometry right now, but it's r dr d theta, and it comes with this little extra r, and you better just remember that. If you think like a pirate, you go r dr d theta. It kind of helps. But it's because there's more to this explanation, but it's because we got different geometry going on. We're doing little teeny sectors of circles rather than little rectangles. So anyway, this is important. This picture's important. I'm going to get rid of some of this though, and I'm going to try to switch this double integral into polar coordinates. Let's see what I got. I got an 8 out front. I got this, which is an a squared minus, let's see, I'm going to do a little fancy algebra here. Let's see, what is this? This is an a squared, oh, here's the best way to do it. Factor out the negative sign and you have x squared plus y squared, right you guys? Mm-hmm. Okay, I just erased it, but what is x squared plus y squared? What is x squared plus y squared?
It's r squared.
It's r squared. So this turns into, if we're converting to polar, there can't be any x's and y's left in this game here. It's going to be all r's and thetas. Okay, so it's going to be a squared minus r squared. Keep in mind, a is a constant. R is a variable now. R is the variable r for my polar coordinates. So this just turned into a squared minus r squared. You guys okay with that? Now what about what's on the end here? What's on the end here? This is my dA, you know, dy dx, dx dy, whatever. It's my dA. What is it going to be now?
R d r d theta.
Yes, it is. R d theta. It sure is. And you know, the extra r comes with the dA, but then once you put it here, now it's really part of the integrand. I mean, it's part of what you got to integrate. So now it becomes part of what I'm integrating. Now check this out. Remember, we're still integrating this region, right, you guys? This is the name. This is the region we're integrating. This quarter of a circle. But now I'm not working vertical. I don't let y move and I don't let x move. I let r move. Now, how does r move? Again, I kind of lost my great picture. R moves from the pole out. I mean, R is this. And R goes from 0 out to whatever curve it hits. So X moves left and right, Y moves up and down, R moves from the pole out. It's like inner to outer. So R moves from here out, and I would say R goes from 0 to whatever the name of this R is that it hits. What is the name of this thing it hits? R equals A. That's the name of it. So it goes from 0 to A. R goes from 0 to A. And then theta, please. Theta. The angle theta, please. What would be bounds for theta, please?
Pi halves. 0 to pi halves.
0 to pi halves. See, actually, now that I'm switched to polar, I wouldn't mind just going all the way around.
Right.
Because 0 to 2 pi, that might be better than 0 to pi halves. 0 to 2 pi. It doesn't matter. I already got it set up to just do a quarter of it. I already got the 8 out there. All right, so we'll just do a quarter of it. We'll go from 0 to pi over 2. That's it. We set this thing up in rectangular coordinates. We realized the integration was going to be horrible, so we switched to polar. And the main thing that dictated that was I was integrating over a circular region. If you're integrating over a circular region, it's good advice to switch to polar. Hey, it's going to be a lot better integral now, but it's still not kindergarten. You know, you still got to know a few things. Let's crank this out and see what our answer is. Do you know how to integrate now with respect to r? Again, this r is part of the integrand here, but it's not in the square root. Any clues how to integrate this guy? Let u equal what's inside the square root there, a squared minus r squared. Du is the derivative. Keep in mind a is a constant, so that's going away. The variable is r. The derivative is negative 2r dr. When I do u substitution, I'm very happy to see that r dr. That's what I wanted. I wanted that r dr to kill that. I move the negative 2 over, though. I say negative 1/2 du is r dr. I replace all this stuff. There's an 8 out here. There's this integral out here. This integral is here, and all this stuff's getting replaced now. What's this turning into? This is turning into a square root of u? Okay, so it's a u to the 1/2. Right, that's what this is. What's this r dr out here? Oh, a du over a negative 2. If you don't mind, I'll pull the negative 2 way out front here. Right, I'll pull a negative 1/2 out front here. That's it, right? That's the r dr. Negative 1/2 du. This is u to the 1/2. There's a d theta out here. Okay, let's knock this out. Let's integrate this thing with respect to u. Man, this is wild. We went from x's and y's to r's and thetas. Then I needed a u substitution on my r's. So now I'm in u's and thetas. But anyway, we're about to get there. This is easy. This is u to the 3/2 times 2/3. That's what happens when you integrate.
Do you add a constant? Or
What did you say?
Do you have to add a constant to that? Or since
No, we got bounds. When we have bounds, we don't put the plus c.
Okay.
We're going to evaluate. We're going to now. So there's the answer. Let's get back to r's. What was r? What was this? What the hell was this u? It was
A squared minus r squared.
oh yeah, a squared minus r squared to the 3/2 from 0 to a. Right? Those are my bounds.
Yeah.
All right, here I am. I'm working on this inner integral. We turned it into U's, we integrated, we turned it back into R's, we're going to evaluate now, here we go. We plug in the A, and we get a big fat 0. Minus, when you plug in the 0, you get 2/3 A squared raised to the 3/2. Right? When you plug in the 0 for R. That's the answer to the inner integral. I got a mess going on here. Hold on a second. I'm going to move over here.
Then you put in, and then you substitute in pi halves and cancels.
Well, hang on just a second. Hang on just a second. That's the answer to the inner integral. Look, and A is a constant, right? So there are no variables left. I'm going to pull, this is a big constant, I'm going to pull it out front. So now, what's out front? There's a -4 out front. Right, because of this. There's a -4 out front. Now I'm pulling this out front, which is multiplied by a -2/3. And by the way, do you know the square root of A squared cubed? The square root of A squared cubed. A cubed. That's an A cubed. That's all out front. Now what's left? I still got an integral from 0 to pi over 2, and I'm integrating with respect to theta. But there's nothing left in there except a 1. All right, here we go. This is the fun part. Integrate a 1 with respect to theta. Theta. Evaluate from 0 to pi over 2. Plug your pi over 2 in there. So cool. We got pi over 2 times this stuff. That's 8/3 A cubed. What is this? The 2 cancels with the 8. 4/3 pi A cubed? Dude. Whew. We did it. The volume of a sphere. The hard way.
Who's the guy that came up with this?
But switching to polar was key. I mean, it made it doable. Look, right? Once we switched to polar, this wasn't that hard. I mean, it involved a nice U substitution here. But it wasn't that hard, right? Switching to polar was awesome. Made this awesome. And we finished. We were able to finish it. So that's what 14.3 is. A lot of polar coordinate stuff. I wanted to finish the problem, but I do feel like I got more to say about polar coordinates. Listen, so you understand, x squared plus y squared equals 16. You know what that is. It's a circle of centered at the origin, radius 4, but if you wanted to convert him into polar coordinates, convert his equation into polar coordinates, it's very easy. What is it?
R squared equals 16.
Good, or one more step after that.
R equals 4.
R equals 4, good, you're right. R squared equals 16, or boom, R equals 4. And you're a circle of radius 4 centered at the origin. You know, some stuff just ain't nice in polar coordinates. Look at this. Here's y equals x squared. We all know what y equals x squared. It's a nice, beautiful parabola. Guess what? In polar coordinates, he ain't that nice. Watch. I'm going to convert him. The way I'm going to convert him is I know what y is. Y is r sine theta. I know what x is. X is r cos theta squared. I had those, remember those ideas? Those were key ideas. I mean, the key ideas are these 3 ideas. X squared plus y squared is r squared, which we've used several times already. But then x is r cos theta, and y is r sine theta. I mean, these are kind of the ideas that help you convert back and forth. So watch what so I replaced y with what he is. I replaced x with what he is, and I could stop here and say, okay, dude, look, you're in polar coordinates. This is a parabola in polar coordinates, which kind of sucks. The truth is, though, once you switch to polar coordinates, you kind of want to solve for r as a function of theta. You know, like with x's and y's, don't you want y by itself as a function of x? Well, when you convert to r's and thetas, you kind of want r by itself. This ain't going to be real pretty. Let me see something. R sine theta, this is r squared cos squared. You know, one way to get r by itself is if you divide by an r right now, which is sort of dangerous in some math, but it's okay in this converting. You can divide by r. One of these r's goes away. Now you just have one r to solve for. Divide by that junk. This r is sine theta over cos squared theta. Yeah, that's the name of a parabola in polar coordinates. That's why when you deal with parabolas, you'd rather be in rectangular coordinates, I think, because they're not too pretty in polar coordinates. Circles? Circles are nice in polar coordinates. So, you know, some stuff just ain't nice. You don't, I mean, really, it's circles. Circles are about it. Except when you study polar coordinates in chapter 10, I don't know how far y'all went with this in Cal 2, there's famous polar shapes. So there's things like the cardioid, they call these limicons. Some of them are a cardioid like that, some of them have an inner loop. There's some spirals, spirally shapes like this, they call these a rose. They've all got special polar equations and special polar shapes. I don't really want to do all this. I mean, I'm switching to polar to help me do double integrals, and mostly for the purpose of these damn circular regions. So I'm not really going to do something over this kind of a region, okay? There's a little bit of pictures like this in your homework. I don't think I assigned much of this. I mean, if you really want to remember polar coordinates, you go back and study all these ideas. I'm kind of cutting down my purpose of polar coordinates just for what I want it for. So I don't want you to go do all that. I mean, you don't need to. For the purposes of what we're doing, we don't have to go study all this. But there are these two. These come up. Watch this. There's this offset circle. A circle that sits out here, diameter 2a. It's centered at a. And it's got a radius of a, and it's centered at a. So it's tangent to. This circle is named r equals 2a cos theta. So that's kind of a famous one. And similarly, a circle that sits on the y-axis here, radius a, diameter 2a, his name is r equals 2a sine theta. So I don't want you to mess with all these crazy polar shapes, but I do like the basic circle centered at the origin, and these can come up. These off-centered circles. But they're not just off-centered any damn where. They're special tangent to the y-axis here, tangent to the x-axis here. These two special kind of guys. They come up. You know what's kind of fun is to convert one of these guys. Do me a favor. Tell me his equation in rectangular coordinates. You guys are smart now. You know what's his center. You know how to write his equation? What's his center?
A.
Yeah, kind of. What's his center? What is his center? Name his center. As a point. What's his center?
Oh, 0a.
0a. And his radius?
A.
A. So could you write an equation for me? For a circle centered at 0a? See, that's centered at 0a, and it's got a radius of a. That's centered at 0a, and it's got a radius of a. Anyway, that's his name in rectangular coordinates. Listen, I'm saying, because he's a circle, we don't want to deal with rectangular coordinates. But watch how you can convert this. Watch, this is so fun to convert him into this. You ready? Let's watch how it converts into this. In order to convert him, I think I'd FOIL this out. You ready? Let's FOIL this out. It's y squared minus 2ay plus a squared equals a squared. I just FOILed this out, you guys. And what's amazing is these a squareds cancel. That's cool. So now I have x squared plus y squared. I'm going to move this to the other side, equals 2ay. Sometimes they look like this. And that's an off-centered circle.
R equals.
Okay, now let's convert to polar. What is this?
That's r squared.
That's r squared, actually. That's r squared. What's, the 2a is a constant, a is a constant. What's y? R sine theta. That's y. So I'm converted.
They are.
I'm totally converted. I was a Catholic, now I'm a Baptist. I'm totally converted, man. No, I'm not. Actually, what did I say? When you convert, you want to solve for R. The easiest way to solve for R is divide by an R right here. It cancels and it gives you one R over here. So R equals 2A sine theta. Cool, you're convinced. That's a circle. Radius A, centered up at 0A, which is what this was. Anyway, we need these these equations, these ideas about circles and how to convert back and forth, I guess. And we need this idea. This is cool. We need this extra R as part of the dA. And then we got to stop when we set these up. We got to quit. We can't think like this anymore. We can't go, oh, how's R's moving like? No, R doesn't move like this. I mean, Y and X move like this, and that's great for the first couple sections. But when you convert to polar, you don't think that way anymore. Now you think from the pole out. You kind of go from the pole out while theta rotates around. It's a different way of thinking to set up your bounds. All right, I'm gonna quit today. Let me get pause. We're off Friday.